Hello, and welcome to Differential Equations. This is lecture 33, Even and Odd Extensions. Last time, we talked about Fourier series. This time, when you talk about relating the Fourier series, Fourier cosine series, and the Fourier sine series. It is common to have a function defined on a finite interval, let's say 0L, then express this function as a linear combination of eigenfunctions of some boundary value problem, and then study the resulting series as a function on the whole real line. This gives us an extension of the function from 0L to the whole real line. Different extensions correspond to different choices of boundary value problems. We'll consider the most common ones. Okay, so first, the periodic extension. Starting from a function f defined on the interval 0L, let's say closed open, let's define f for other values of x by requiring that the equation f of x plus L equals f of x always hold. Thus, for example, if you want to compute f of 3L over 2, well, you recognize that as f of L over 2 plus L. And so by this equation that we're imposing, that should be the same as f of L over 2, which we already know. indeed, f of x plus L equals f of x immediately tells us the values of f on the interval L to L from those on the interval 0 to L. And then it tells us the values of f on the interval 2L to 3L from those on the interval L to 2L, and so on. The graph of the periodic extension of f consists of copies of the graph of f translated one after the other. So for example, if we start with, say, something that looks like this, between 0 and L, this would lead to right, going from 0 to L, and here we're going, well, let's move the axis to here. So 0 to L to 2L, 3L, minus L, minus 2L, and so on. Right? Note that even if f is continuous, on 0L, its periodic extension will typically have jump discontinuities at plus minus L, plus minus 2L, plus minus 3L, and so on. All right, so indeed in this case, we have a jump discontinuity at every one of these multiples of L. The periodic extension of f from 0L corresponds to the Fourier series of f on 0L. Indeed, suppose that a0 plus the sum n goes from 1 to infinity, an cosine of n 2 pi over L x plus bn sine of n 2 pi over L x is the Fourier series of f. Notice the difference here. In the last lecture, we were working with the interval 0 to L, and so we had n pi over L times x. Here, because we're working with 0L, it's 2 pi over L that shows up in the cosine and sine. But indeed, if this is the Fourier series of f, then we know that this coincides with f on the open interval and is periodic with period L. Note that at plus minus L, plus minus 2L, and so on, the Fourier series converges to the average of the left endpoint and the right endpoint, or the right limit. And so at these points, it may differ from the function f. Okay, but except for these problem points, the function you get from taking this Fourier series is exactly the periodic extension of the function you started with. Okay. So next, we're going to consider periodic extensions of f to functions that are even or odd So let's start by talking a little about these. Okay, so a function h is said to be even if h of minus x is equal to h of x, and odd if h of minus x is minus h of x. So for example, suppose that h of x is just a power of x, then h is even when n is even, h is odd when n is odd. And this is where the name comes from. We call them even function and odd functions because if you just have a monomial, then it's even when the power is even, odd when the power is odd. Right? And also, so another important example, h of x equal to cosine lambda x is even, and sine lambda x is odd for any lambda not equal to 0. The graph of an even function is symmetric with respect to the y-axis, while the graph of an odd function is symmetric with respect to the origin. So for example, if you have something that looks like a parabola with minimum at the origin, or if you have something that looks like the graph of cosine, and these are even, and they're unchanged by reflection across the y-axis. Right? On the other hand, if you have something that looks like the graph of, say, a cubic polynomial, or if you have something that looks like the graph of sine, and these are odd, and here it's unchanged by reflection across the y-axis, followed by reflection across the x-axis. So you need to do two reflections before you get the same thing. So if you started with something like this and you reflected it across the y-axis, it would look like this. But then if you reflected this way and then reflected down, you get that. Same thing here. If I reflected it across the y-axis, I would end up with something like that. But then if I start with this and I reflect that across the x-axis, then I end up with this. Okay, one property that we'll be using is what happens when you integrate on an interval that is symmetric around the origin. So first note that for any function h, if you integrate between minus L and L, then what you can do is write this as an integral from minus L to 0 plus an integral from 0 to L, right? And now what I'm going to do is I'm going to change variable in the first integral to minus x, right? So I'm going to end up with, okay, let's see what happens to the endpoints. If x was equal to minus L, then s is equal to L. And if x was equal to 0, then s is also equal to 0. Then I have h of minus s, and then I have minus ds. Right? And then the other integral I'm not changing. Okay, so now what I can do is if I change the order of the endpoints here, I have to pay for that with a minus sign, but I have a minus sign to spare right there. So I can write this as an integral from 0 to L of h of minus s ds plus the integral from 0 to L of h of x dx. Right? Now, this s and this x, those are both just dummy variables, right? I could integrate over tau from 0 to L h of tau d tau, and that would be the same as integrating h of x dx, right? So I can change the integral here to be, instead of with respect to s, to be with respect to x, same variables I'm using in this other integral. And so I can write these together as the integral from 0 to L of h of x plus h of minus x dx. Okay, so I'll put this down here. So if h is even, then the integral from minus L to L of h of x dx is, well, h of minus x is equal to h of x if h of x is even. So this would just be 2 times the integral from 0 to L h of x dx. And if h is odd, then the integral from minus L to L of h of x dx, well, in that case, h of minus x is minus h of x. So that just cancels and you get 0. Right? Let's think about that in terms of the graph. So this, if I have an even function, right, then this says that integrating from minus L to L is the same as doing twice the integral from 0 to L. So if you think about integrating from 0 to L, right, that would be the area under the graph here. If I were to go from minus L to L, that would be this area under the graph and this area under the graph. And what we've just computed is that this area under the graph is the same as this area under the graph. So you might as well just compute this one and multiply by 2. Meanwhile, over here in an odd case, this says that if you integrate from minus L to L, then this area is the same as this area, but with the opposite sign. So the integral just cancels out. This cancels out with that, and so you integrate to 0. Okay, so finally, let's point out that the product of 2 even functions or 2 odd functions is even while the product of an even function with an odd function is odd. Okay, so that's really easy to see. If you had two odd functions, say, right, so let's say h1 and h2, and you evaluated at minus x, you'd have h1 of minus x times h2 of minus x. But because they're each odd, that would be equal to minus h1 of x times minus h2 of x, and minus is plus. So we end up with an even function, right? And similarly, if you had two even functions or an even function times an odd function. Okay, so with that discussion out of the way, now let's consider the even extension of a function f defined on 0L. Okay, so if we want to extend f to an even periodic function, then we can start by extending f to minus LL by requiring that for x's between minus L and 0, it satisfy f of minus x, or f of x is f of minus x, right? So if you give me an x satisfying this, and I want to know what should f of x be, I declare that it's equal to f of minus x, and minus x would be an x living here where we already know what f is. This is the same as saying that we reflect the graph of f across the y-axis. So for example, let's take the same graph that we had up here. So suppose you start with this, right? And so what we would do, go to minus L, and then we would extend this so something like that. Next, we take the function, let's say, the extended function, defined on minus LL, and extend periodically the whole real line with period 2L. Right, so in the case of our example, looks like this. Here's 0, L, 2L, 3L, 4L, 5L, minus L, minus 2L, minus 3L, and so on. And notice that this one does end up being continuous. To express this in terms of eigenfunctions of some boundary value problem, there are a couple of things we could do. The simplest way to proceed is to use that every cosine of n pi over L x is an even function. So if alpha naught, let's say, plus the sum n goes from 1 to infinity of alpha n cosine n pi over L x is the Fourier cosine series of f on 0L, then it coincides with f on the open interval 0L is an even function and is periodic with period 2L. Thus, the Fourier cosine series is equal to the even periodic extension of f. Okay, another way we might obtain the even periodic extension of f is to first extend f to an even function on minus LL as above, and then take the Fourier series of f on minus LL. So to compare these, let's denote the Fourier series by a0 plus the sum n goes from 1 to infinity of an cosine n pi over L x plus bn sine of n pi over L x. So side note, note that we're back to using pi over L instead of 2 pi over L because this interval has length 2L. So let's denote the Fourier series by this, and let's compute the coefficients, right? So first, a0 would be 1 over 2L times the integral from minus L to L of f of x dx, right? But we're computing the Fourier series of our extended f to minus LL, and we extended it to an even function, right? So because this is an even function, I can write this as 1 over L times the integral from 0 to L of fx dx, right? Because we saw that if you have an even function and you're integrating it from minus L to L, that is the same as twice the integral from 0 to L. So that's since f is even, right? An 1 over L times the integral from minus L to L of f of x cosine n pi over L x dx. Right? This would be 2 over L, the integral from 0 to L of f of x cosine of n pi over Lx. Since f of x times cosine n pi over Lx is an even function, and then Bn, 1 over L, integral from minus L to L, f of x sine of n pi over L x dx is equal to 0, since f of x times sine of n pi over L x is odd. And we saw that if you integrate an odd function over an interval symmetric around the origin, you always get 0. Thus, after extending f to minus LL as an even function, its Fourier series is just a0 plus the sum n goes from 0 to infinity, an cosine n pi over Lx, right? So only the cosines survived this integration with the same coefficients as the Fourier cosine series of f on the interval 0L, right? So we recognize this and this as exactly the coefficients of the Fourier cosine series on this half interval, right? So that is to say, the two ways of obtaining the even periodic extension of f coincide. As well they should. Okay, so finally, let's consider the odd periodic extension of a function f defined on 0L. If we want to extend f to an odd function, odd periodic function, then we can start by extending it to minus LL by requiring that if minus L is less than or equal to x less than 0, then f of x should be equal to minus f of minus x, right? So this will guarantee that it's odd, and this tells us what to make f of x, because if x is in between minus L and 0, then minus x is in between 0 and L, and so we know f of minus x in that case, and this formula tells us what f of x should be. This is the same as saying that we reflect the graph of f across the origin. So let's do an example, and let's use the same starting piece as we had over here. So for example, you start out with something like that, then right, so we started out with something that looked like this. This up a little bit. Okay, so I'm going to reflect it first across the x-axis, the y-axis, and then across the x-axis. Right? And I only keep that second one. So here is minus L, 0, and L. Next, we take the resulting function defined on minus LL and we extend it periodically the whole real line. With period 2L. So in this case, we have this as our building block. And it would just get repeated. Over and over. And so here's L, 2L, 3L, 4L, 5L, 6L, 7L, minus L, minus 2L, minus 3L, and so on. To express this in terms of eigenfunctions, of some boundary value problem, we again have a couple of ways to proceed. The simplest way to proceed is to note that since every sine of n pi over Lx is an odd function, if some n goes from 1 to infinity of, let's say, beta n sine of n pi over Lx is the Fourier series of f, then it coincides with f on the open interval 0L, it is an odd function of x, and it is periodic with period 2L. Thus, the Fourier sine series is the periodic, the odd periodic extension of f. The other thing we could do is to first extend f to an odd function on minus LL, and then take its Fourier series. Right. If we denote the series in the usual way, and compute its coefficients, we have that A0 would be 1 over 2L times the integral from minus L to L f of x dx, which would be 0, since f is odd. An 1 over L, integral from minus L to L, f of x against cosine n pi over L x dx would also be 0, since f of x times cosine pi over L x, this is the product of an odd function with an even function, and so it is odd. And then Bn, 1 over L, integral from minus L to L, f of x sine of n pi over L x dx, this would be 2 over L, integral from 0 to L, f of x sine of n pi over L x dx. Since the product of an odd function and an odd function is even. Thus, after extending f to minus L as an odd function, its Fourier series has the form sum n goes from 1 to infinity Bn sine n pi over Lx with the same coefficients as the Fourier sine series of f on the initial interval 0L. That is to say, the two ways of obtaining the odd periodic extension of f coincide. Okay, and this shows us the relation between Fourier series, Fourier sine series, and Fourier cosine series, right? The latter two are particular cases of the first when you're working with odd functions or even functions. Okay, and we'll stop there, pick it up next time.